let me unpause or let me stop sharing for just a minute, just to see how we're doing. And so I can see the chat too. Yeah. I love the chat. You guys, you put one Beatle up and then you want them all. Best Beatle. I think so too. I like George. I like Ringo too, though. You're right. Ringo's a cool dude, but I like George. I like George's music, but Ringo's good. I thought that song was appropriate for this time of year since the sun's starting to pop out, so that's why I played it. I will pin it to myself, so that way you guys don't have to worry about if I can find myself. Where am I? There I am. Okay. And I didn't start my video, but now my video is on the paper. We went over this last time, and I know you guys have been begging me, and you're probably mad at me because I haven't put up these notes yet on Brightspace, but I will before Friday. I promise you I will do it before Friday. I'll try and get them done all scanned in today and posted, but I'll organize all of the ones that I've got and post them, so don't worry about that. We went over basically how to do the homework. We almost took 2 days to do it, but I wanted to ask if you guys have any questions about that before we continue. If you got any homework questions, I can answer them today before we get going. Anybody? I'll give you a minute if you're writing in the chat box. You guys learning anything in this class?
Yes.
Yeah. Yes, that's a good sign. Okay. That's good. So I am teaching you guys something. A lot of excellence, a lot of Excel stuff. Excel is very useful. You will probably, if you're, working, doing any kind of data analysis, but even just calculations, you may end up using Excel a lot. The other thing you do as an engineer a lot is write. You have to write technical reports. If you go into academia, you have to write papers and other things, but you're always explaining what you're doing, and so you end up writing a lot and creating figures and creating tables and all of this stuff. So if you can create a table and a figure in Excel, you can export it into a Word file easily as long as you've created it the right way. So a lot of what I've been trying to stress is presentation of data, so that you are good at that, because in engineering, that's a lot of what you do is presentation of information so that others can act on it. I will share my screen again. I don't see any questions, so I'm going to share my screen again because we need to finish these notes. And before we finish the notes, I want to, nope, where is this? I'm in the wrong handouts. Here's streams. Okay, so last time we were talking about these notes, we developed this equation. This equation is the classic Streeter-Phelps equation. It was developed in 1958. So if you think about 1958, this is pre-EPA. When did they start doing a lot of construction of wastewater treatment plants in the US? It was after World War II, in the 40s, the 50s, the 60s. That's because they were finding, hey, we got lots of dead fish all over the place. We're discharging too much sewage. And at that point, they had primary treatment plants. Primary treatment is just settling the solids that are in the wastewater. and the remaining water still has maybe 100 milligrams per liter BOD. So if you discharge it to a stream and it gets diluted enough, it may not kill any fish, but it's still not that great because it still stresses the environment quite a bit. So after the Second World War, that's when we started building secondary treatment plants with activated sludge to process it, and then a final clarifier, final filter, which is basically settles the biomass, and then the water comes out of there fairly clear. It's still not completely treated because you can still have pathogens in it. So a tertiary treatment is where you now disinfect the water or do some other treatment past just the secondary settling. So you have primary settling, secondary settling, and then some process afterwards. And now we have advanced wastewater treatment plants where we can even put reverse osmosis on as a final stage and then reuse that water for some purpose. And in some cases, it can even be re-drinking the water that was wastewater. What's the ad for Ivory soap? Anybody know? The original ad for Ivory soap. Let me Google. How do you spell ivory? Purity. Ivory soap. Here we go. The original Ivory bar soap was developed in 1879 by Harvey Procter. It was developed with pure and purposeful ingredients. It was meant to be a staple in the home and mild enough to use as a whole family. Ivory was pure, 99.44% pure to be exact. For years, they marketed this soap as being so pure because it's 99.44% pure. Okay? Remember that number. I'm going to take this page here. .44% pure is Ivory soap. That means it has 0.56% other stuff in it. That's 0.56 out of 100 grams out of grams, or grams if we know that the density of water is 1 gram per milliliter. We know that this is 0.56 grams of other substance per 100 milliliters of soap or of water. Right now I'm saying let's convert this into a liquid phase, into a water phase. If we had that much impurity in water, how much would it be? Well, in water, if we had that much impurity in water, we would have 0.56 grams per 100 mLs. That's 5.6 grams per 1 liter, because there's 1,000 milliliters per liter. So wastewater, when it reaches the municipal wastewater, when it reaches the wastewater treatment plant, is typically 200 milligrams per liter as BOD. It's also typically 200 milligrams per liter as suspended solids, SS. So 200 milligrams per liter, look at the difference there. It's kind of amazing because you think of Ivory soap as being pure soap. It's got some crud in it. It's got more crud in it than wastewater has waste in it. As environmental engineers, we are working with trace quantities often. This is milligrams per liter. We're trying to get this down to about 10 milligrams per liter before we discharge it to the river. So we're talking about taking out almost all of this BOD out of the water. Not quite all of it, but, you know, and in fact, our nitrogen, our new phosphorus regulation is 1 milligram per liter, or 0.1 milligram per liter as phosphate. We're talking, this now is 100 micrograms per liter, which is parts per billion. Milligrams per liter are parts per million, right? This is a milligram per liter is a part per million. Microgram per liter is part per billion. So that's 100 parts per billion. Okay. We even go down to hormones in the environment that are nanograms per liter. And at those concentrations, they have effects on fish and other animals in the water. So we're often dealing with trace quantities in water that still can create problems. And so 200 milligrams per liter, yeah, that's actually quite a bit, but it's actually not as much as impurities in ivory soap, which is claimed to be 99.94% or 99.44% pure. Okay. Share contents. So here, this equation, why was it developed? Because in science, the question is always, okay, we're going to build a wastewater treatment plant. How big do we need to build this plant? How much do we need to remove? What do we need to get the BOD down to? And it comes back to this deficit question. How much deficit can we allow in the stream before we start killing fish or affecting organisms? So this equation becomes our first water quality model. It was the first model used by the precursor of the EPA, the Public Health Association, to basically help design treatment plants to say, okay, we have this much sewage going into the stream. This is the flow of the stream. This is the flow of the pipe of the sewage going into the stream. If we reduce our BOD, our L naught, going into the stream to this point, we will not create a large deficit in the stream or a big deficit in the stream. And we can regulate it now because we have a model that says, hey, L naught affects the value of D. It's a function, D is a function of L naught. It's also a function of reaeration and these rate constants. So we have to estimate these rate constants too. We also have to know something about the flow of the stream and everything because we're interested in where does this deficit occur downstream. So this is a classic Streeter-Phelps equation developed by Streeter and Phelps, who work for the Public Health Service. And since that time, it's like been modified and upgraded to include lots of things. And in fact, on this, in this handout on streams, if you go down to the very last page, this is 1987, Major Constituent Interactions in Quality, which is a river water model developed by Brown and Barnwell. These two guys worked for the EPA, actually in Athens, Georgia. They were still there when I got there in the, when did I go? I went there in the late 80s. So they were developing this model about the same time that I got to the lab where they were doing this. But it basically is an EPA model, Qual2E, that states would use to run to see, okay, if we're going to build a treatment plant, how big does it need to be? But it also allows you to do waste load allocation. If you've got 5 industries on a river and they're all discharging to the river, well, how much waste can each discharge to the river? So it's not just one plant, it's like a series of plants along the river, or a series of wastewater treatment plants along the river, so that you can say, well, if you know, equally based upon your flows, based upon everything else, this is how much each of you can discharge to the stream. If you look at this model, you see arrows. You guys know what these arrows represent. They represent kinetics. You know what these terms represent, these alphas and betas. They represent factors that affect this rate constant. Over here, you've got some simple ones that you already understand. KD is for BOD. KB is a sediment organic, this is biochemical oxygen demand. This is sediment demand. So this is actually not settling a BOD. This is, if I've got lots of sediment in the stream, those sediments are taking up dissolved oxygen also. Okay? Here's algae. They've thrown algae into this model because algae can produce dissolved oxygen. Algae can respire dissolved oxygen, and they can uptake dissolved oxygen. So this is a diurnal transfer of oxygen. During the day, the algae are producing it. At nighttime, the net is, and these are net because during the day they're using it, both using it and producing it. At nighttime, they're not producing it, but they're still respiring. Over here, you've got nitrogen. Over here, you've got phosphorus. So they've thrown in some nutrients into this model. Atmospheric reaeration, Ka. We've got Ka and Kd in our Streeter-Phelps equation. The Streeter-Phelps equation is so simple because you only have this term, you only have this term, and then you also have this term, Ks, which is BOD precipitating out. If it's solid particles, it will precipitate out. So we've got 1, 2, 3 of the rate constants from the Streeter-Phelps equation, only those 3 in this. But the model includes a lot of other things because, hey, we can throw in dissolved oxygen is affected by nitrification, for example. Remember, this is carbonaceous BOD. But over here, we've got ammonia being converted to nitrite, being converted to nitrate. And so these beta 1s and beta 2 are rate constants for that conversion. And in the process, it's ammonia plus the dissolved oxygen forming nitrite. Nitrite plus more dissolved oxygen forming nitrate. And then these, hey, algae takes up the nitrate and grow. Algae takes up the phosphorus and grows. And so algae are growing. They're also settling out because they die and then settle and go to the sediments. So we've got a loss term here, basically because of algae dying and becoming part of the sediments, the biomass within the sediments. And that creates some of this demand then. So you can see this as a little schematic of all of these rates, and basically we can write differential equations on all of these things. So we can take the Streeter-Phelps equation, which has 1, 2, 3 terms. We can expand on it and actually model not just dissolved oxygen and BOD, which is what we're doing in the Streeter-Phelps equation, but now we can model the nitrogen, we can model the phosphorus, we can model the algae. And in more complex models, let's take a more complex model. I was doing some things here on, this is CADM, Center for Water Research in Australia. Here's a basic model that it does, but it does a lot more fancier things than that. I'm always covering this up. This is the this is in New Zealand where they're using this model, and it just gives you some information about the model and everything else. Water Quality Modeling Group, U.S. Geological Survey has a water quality modeling group. They have partners, publications, things, you know. They use HEC-RAS, which is basically a hydrologic model. It has some environmental stuff in it, but it's mostly water routing. here's CE Qual W2, which is an update of Qual 2K that I just showed you. So modeling tools used include this, Sparrow, Prism. You get the idea. There's all of these models that people have developed. And so if you understand the basic, structure of these models, and that's why I've been going through like Streeter-Phelps, because hey, we got 1, 2, 3 ray constants here. We solve for it analytically, but we don't have to solve for it analytically. We can solve for it numerically. Once you get a model that is this large, you don't solve for it analytically. You have to write numerical code and solve for it using a numerical method that solves ordinary differential equations. Something like Euler's method, but probably something a little bit more complex than Euler's method, because you may want to use a predictor-corrector method rather than the simple first-order. Euler's method is basically a first-order Runge-Kutta method, and sometimes they use fourth-order Runge-Kutta methods and other things. So there's all of these classes that you can take on numerical methods, even if you're into all of this modeling stuff. Okay, let's go back to this CADM stuff. So here's EPA's site for surface water quality modeling, and they do training on this. So you can go for a day and learn how to use these models, how water quality models are developed, data needs for models, nutrient cycling, potential impacts on water quality, developing nutrient endpoints, modeling Florida lakes with bathtub. So that's a clever name for a model, is bathtub. Dissolved oxygen modeling. These are actually YouTube videos that you can watch on these modelings. Sediment models. They have models that are just on cycling of nutrients and contaminants within sediments. WASP is a model. It's a water quality assessment. I think it's a lake model. I'm not quite sure. I can't remember. SWOT is a model. SWOT was actually developed in our ABE program, but it's a different kind of model because it mainly is a routing model, but it also accounts for solids running off and things like that. So it's mostly hydrologic, just like HSPF is a model. So these are watershed models rather than just individual stream models. And a lot of these are because they're for stormwater management, like SWIM, which is basically water routing rather than nutrient or other things. This qual, anything that's a qual, like Qual 2K, Qual 2E, those are water quality models, not necessarily where maybe you're assuming that the flow is constant. Okay, let's go back to the notes. So I think I've convinced you now that this model is very simple. It's got 3 rate constants, Ka, Kd, and Kr. Kr, remember, is a combination of Kd plus Ks, the settling rate constant. So we have those 3 rate constants within this one. We solve this. This is the analytical solution to this problem. We could go back up here and take the 2 basic equations on L and on D. Where's my D equation? On D, this one, and we could solve them numerically using Euler's method or anything else that we wanted to too. We could even bring back, and what some of these models do, they bring back the fact that it's a function of time and it's a function of distance. So we don't have to necessarily have a constant input. We could make this a partial differential equation, the change in deficit with time and the change in deficit with distance along the stream reach. Streeter-Phelps, again, assumes steady state. So that means that they're assuming that this L naught is a constant value within the stream at a certain point. And that point is a discharge point where you're discharging water to the stream. Because, hey, you're assuming that you have an industry or that you have a wastewater treatment plant that is on a daily basis putting in about the same load of BOD into the stream. Okay, so the L0 is milligrams per liter after it's mixed and everything else within the stream. Okay, so this equation, this is the decay of the initial deficit. This is production of deficit through BOD consumption on the waste that you're discharging, on the L0 that you're discharging. And then this is the decay of the deficit because of reaeration from molecular oxygen in the air going into the stream. So we need the reaeration coefficient, we need Kr, we need Ks. So evaluating the constants, we can get some from field data, we can interpret and get KD from bottle if we do BODs in the lab. The literature Ka, and in your notes now I've added this, which are reaeration formulas. These are older formulas, but they haven't changed much because O'Connor Ka, the reaeration rate constant, is a function of the oxygen diffusivity, the velocity of the stream, and the height of the water column in the stream. This is like the average height of the water in the stream. So to the 1.5 power. So this is an empirical equation. Even though the units all work out here, as long as you use the diffusion coefficient and feet squared per hour, mu is the average stream velocity in feet per hour, and then the height is in feet. So if you calculate this all out, feet disappear from the equation, and you just have per hour. So the Ka is measured in per hour, okay? And another form where they get rid of this diffusive coefficient by just plugging this number in and rearranging it, you get this, where mu is in feet per second, h is in feet, and K is measured in per day. So you have to plug the number in here for mu in feet per second. You have to plug in the height in feet, and then Ka magically comes out in per day, because this 12.9 has unit conversions on it that are not explicitly given in this equation. So you can do this or you can do this. They give you the same value, but just note that this one, hey, the units on here don't agree with the units on this side, because it's 12.9 has units that are not written down, okay? Churchill has a formula. You can tell that all of these formulas are about the same. The higher the velocity of the stream, the higher the Ka value. More reaeration if the stream is moving faster. That's because there's more turbulence in the stream, more turnover, more ability for oxygen in the air to transfer into the stream. The height of the stream then, as the height increases, the oxygen transfer rate decreases, because obviously the thicker the water column, the less transfer I get per volume of water within the water body. So these equations kind of make sense. Where you get large Kas and it's hard to model is over dams, because if I've got a water flowing over a dam, you get tons of reaeration at that point because of the turbulence and the entrainment of air into the water and everything else. So low dams that have turbulence in them are very, very beneficial to transfer oxygen into the stream. Or if you've got a steep mountain stream where you've got water going over rocks, obviously you've got a huge Ka. So some of these equations were developed under different conditions. Owen's formula, calculating reaeration. Owen's equations developed down shallow streams, fast moving. So Owen's equation would be best to use if you were doing like a mountain stream or something like that. But they give you all about the same value for reaeration coefficients. So reaeration coefficients, hey, literature, some formula that you can calculate a reaeration coefficient. It depends upon mixing blocks, velocities, temperature, wind speed, morphology, surface films, ice cover, things like that. And then there's other formulas too here. You know, there's a whole bunch in the literature. Now, DC here, the deficit with a sub C means a critical point. Because at some point, our deficit curve, if we don't have a good water treatment plant, this deficit is a maximum value at some point. Let me see if I have a graph. Yep, I do. This is our oxygen solubility, or this is our oxygen curve, because if we've got waste coming in at this point, at this distance, downstream from that distance, our oxygen is being consumed along here the whole way. Well, the oxygen gets consumed, and the oxygen in the stream keeps going down and down and down until eventually the oxygen consumption equals the reaeration rate. Okay? At this point, the deoxygenation rate equals the reaeration rate because it's flat. Change in oxygen concentration over change in distance is 0 here. If we go up to our original equation here, where is it? This equation right here, if we look at this equation right here, if the change in deficit over the change in distance is 0, that means this term equals this term. Okay, which means also up here, this term is 0. Change in deficit with distance is 0, which is at the minimum value of that line. That means the rate of BOD utilization, KD times L, is equal to the rate of oxygen depletion, or excuse me, reaeration, which is Ka times D. So this is oxygen consumption, this is oxygen production through reaeration. And so this term equals this term at that point. Okay? And then beyond that term, reaeration is greater because our L is so low now. Our BOD in the stream is so low that we don't have much of this occurring anymore. We still have some of this occur. We still have reaeration occurring. And our stream is recovering up at this point because most of the L has been consumed because we didn't plot L, but if you remember L, it's just a first order decay as a function of distance in the stream. So at some point it gets really, really low, and that's when reaeration kicks in and our oxygen concentration in the stream goes up. So this curve is known as an oxygen sag curve as a function of river mile or distance downstream. And this is a critical distance. So this is the point we're interested in. Because if this is too low at this point, we get fish kills. So you don't get fish kills right where the water is going into the stream. You get the fish kill downstream after a lot of the oxygen has been consumed and taken out of the river. So it's downstream you have to worry about. And then further downstream, hey, all of the BOD is consumed and we're recovered. Our stream is recovered. Okay, so this is oxygen sag. Remember, the deficit is the difference between the saturation value, this line, and this line. So the difference between this and this is our deficit. So we can plot the deficit as a function of time, and the deficit has the maximum value. So this CD is the critical deficit. Critical deficit at this point is where this is equal to this. Again, reaeration equals oxygen depletion. And it's that point. So now we can sense the critical deficit is equal to this point because we can rearrange that. We know that this term equals this term. We can substitute in L naught E to the blah, blah, blah here for this. That's what we've done. And we've rearranged it, brought the Ka, which was multiplied by here, over. And now we can define the critical deficit point as being equal to this term. We also know that the deficit is equal to this term. So we can set these two equal. Where does our critical deficit equal our deficit? Well, where this side of the equation equals this side of the equation. Set equal and solve for, and to do this, we're basically getting rid of D, but we still have X. So we have an X here, an X here, X here, X here. We can solve for X. So you do that and you end up with this. The distance, this is the distance of the critical deficit. So now, if we know all of our parameters in our Schroeder-Phelps equation, our velocity, our rate constants, we can solve for the place where the critical deficit occurs. We can solve for XC, the distance downstream at which the critical deficit occurs. Well, if we know the deficit, that point now we can go back in this point, plug in that value of X, and solve for the deficit, which is now the critical deficit, because it occurs at the distance where the critical deficit occurs. So we can just simply substitute back in now to solve for the critical deficit, okay? And we will get this value here. So it occurs at this point, critical deficit equals, or the change deficit equals this, critical deficit equals this. This is, I think this term right here is if you don't have any initial deficit. So I've got it in a couple of things here, because in normally you would substitute it in here. If you don't have any initial deficit, this term goes away, okay? But the point is in modeling this, you're interested in this point because that's the worst case scenario. You want to avoid a deficit that is going to kill fish or affect things downstream. And typically now with water quality models, we don't have to worry about this because the regulations on discharge of BOD from rivers are stringent enough that we don't get a typical oxygen sag curve in rivers, unless you've got lots and lots of industries along them or something like that. But the treatment is such that now we're worried about emerging contaminants and other problems, pathogens too, and that's why we have disinfection rules now in wastewater treatment plants. We used to not have disinfection rules. That's a new thing over the last decade or so, where you have to disinfect the water before you discharge it to the stream. And now people are worried about hormones and pharmaceuticals and other things in the water because, hey, the water coming into a municipal waste treatment plant is contaminated with all of the, people are taking medicines, and have those medicines go through your body. They end up in the toilet. You flush the toilet. They end up at the waste treatment plant. And now you've got all of these pharmaceutical chemicals, including hormones, that if they're not removed by the wastewater treatment plant, they end up in the river and can affect organisms in the watershed. Okay, so there's a lot of papers lately on that, not just on oxygen. The problem used to be oxygen. Now it's these micro concentration, or I should say nanogram and picogram concentrations of chemicals that people are worried about that have effects at those levels. Critical conditions, summertime, maximum temperature conditions. Critical conditions, summertime, maximum temperatures. I'm going to show you a paper because we have 10 minutes left, 9 minutes left. If I can find it. Here's your homework. Let's go back up here to Werner. This is supplemental. Where's the other paper? This is time series. I don't want time series. I want this one. Come on, where's the paper? It's 2016. Here it is. This is a paper that Julia wrote. Julia is her middle name, but she goes by Julia. She was a PhD student of Professor Nyes and myself. She just graduated not too long ago. She's doing a postdoc in Chile. She's from Argentina. And she did this water use assessment of the Wabash River. And what she did was she evaluated all of the NPDS, that's National Pollutant Discharge Elimination System, discharges. The EPA regulates anybody that discharges into a water body. And so you have to get a permit if you want to discharge water into a water body. And all that permit information is publicly available. So here are all of the significant that you have to let them know about it too, and you have to get a permit. And the permit, that's a permit that the wastewater treatment plant gets to discharge BOD, suspended solids, certain pesticides, pH. You know, in other words, the water has to be between a certain pH range. You can't discharge acid to the Wabash River. So they write the permit based upon the water, the volume of water that you're discharging, and where and in what water stream you're discharging it to. So, and they have to do, look at all of the discharge points here. They have to do wastewater allocation. How do they do wastewater allocation? They run a model to say, if all of these plants are discharging water to this stream, hey, our stream won't be affected because we've restricted what each of these plants can discharge to the Wabash River. This is actually the main stem of the Wabash River over here. It actually is this one. It goes all the way over to Ohio, comes down, and then for a while is the border between Illinois and Indiana, right in this range. What she did was she compared these withdrawals from the watershed to these discharges to the watershed, just to see what the mass balance looked like. And what you see is in the summertime, she got flow data from the USGS. I don't need to say too much about that, but here's stream flow on this side. This blue line is a monthly stream flow average for this 1 year. And you can see in August, September, October, the stream flow is very low. January, February, and this varies by month or by year too. But we have March and April rains here. Look at how high the stream flow is. It's high. And this is at the discharge point. This blue line is at the discharge point for the Wabash River. So the flow in the Wabash River changes daily, and it depends upon how much rain we get. There's always some base flow in the river. So even if we don't get rain for a month, you have groundwater infiltrating into the river so that there's always water flow into the ground, into the river. And in fact, if you think about it, the river is the groundwater level because you have water under the banks. And if you dig down, you'll be right about the water level of the river. So the river, think of it as an outcropping of the groundwater in a way. But you can see in the summer, we have low flow conditions. And this is typical of most streams in the US, is the low flow conditions occur in the stream because you get a lot of evapotranspiration off of the farm fields. You don't have as much runoff off of the fields, off of the land in the summer as you do in the wintertime. In the wintertime, even in January, sometimes you get frozen ground. So if it's raining, that water is going directly to the stream. And in March and April is typically when we have a rainy season. And so you end up with very, very high stream flows in the spring months, and in the winter months, and then in the summer it goes way, way down. So where do we worry about discharging waste? It's in the summer months. The summer months is where it's critical, because if we've got lots of BOD coming in, there's not much water in the river, and that's where we can have major contamination issues. What Julia did here, which is interesting, is this is percent of stream flow contributed by discharge. It goes up to 100% here. That means in September of this year, 100% of the stream flow was because of the discharges. All of these discharges to the river are what's creating the stream flow. So West Lafayette discharges water. We're taking out water, and then we're discharging the water. So it's not like it's not water from the Wabash River. It's water from the Wabash. We're pumping it out, and then we're discharging it back into the river. But it means that we pumped all of that water. Before it gets to this point where it enters the Ohio River, we've extracted and pumped the water uphill and then let it flow by gravity through the wastewater treatment plant back into the river. We've basically pumped this whole river. The volume exiting here, we basically pumped that whole volume at some point in the watershed in the summer months. We've literally used 100% of the water, okay? And yeah, some of that water we may have used 2 times, some of it we may not have used at all, but on average, we've used the water once in the watershed, in a treatment plant, in a drinking water plant, in a factory, or something else. Okay, so that gives you an idea. We use all. You think we have unlimited resources of water in the Midwest? Well, we kind of don't, because hey, we're using it all at least once. If you think about this, then how many times does the water used before it reaches New Orleans? When they're pumping water out in New Orleans, all that water has been used upstream someplace. Okay? So that's my story, and I'm sticking to it. Any questions? It's time to go. No questions? Okay, definitely do your homework, or start the homework before Friday. Start each problem so you can ask me questions on Friday if you got homework problems, because it's due on Monday. Okay? So I'll see you guys on Friday then. You guys have a good day too. Yep, we'll see ya.